Hi, everyone. My name is Ryan Doty. I'm a solutions architect here at AWS, and I just want to say thank you for taking the time to join me on this webinar. I'm really looking forward to covering workload optimization with no architectural changes. To get today started, I thought I would highlight a brief agenda, and I'd like to cover this in a couple of different topics just to make sure that's clear in terms of the direction we're going in today. So the first aspect of this is I'm just going to highlight what we're solving for, broad categories, to make sure that it's crystal clear what we're trying to achieve through this webinar. Secondly, we'll go through a plan of action in the sense of diving into the specific areas that we're going to make changes to solve for some of those problems that I'm going to highlight on the next slide. Again, the goal is to make this actionable, so I do want to cover for a couple minutes just the tools that I will use throughout today's webinar to make sure that you know the tools and you can go use them after the conclusion of the webinar. Then we'll spend some time diving into the specifics, specifically Amazon Elastic Block Storage, Amazon Relational Database Service, or in Amazon Aurora. And then lastly, we'll finish up with Amazon Elastic Compute Cloud, showing how we can solve some of these problems through those services. And then last but not least, we'll wrap things up with just a where to start to give you an idea of where you can go after this webinar to make sure that you recognize some of the problems that we're solving today. So I'd like to start off by just giving a high-level introduction to the problem that we are aiming to solve to ensure this is a more cohesive presentation. With this in mind, I've broken up the presentation to solve 4 distinct problems. The first, and most likely the largest priority for organizations to solve currently, is cost optimization. Throughout today's presentation, I'm going to make an effort to walk through a variety of changes you can make to your existing AWS footprint to recognize some easy cost savings. Some of these changes can result in savings that can be recognized theoretically overnight. Second, I don't want us to only recognize cost savings because ultimately, if we recognize cost savings but did not have the performance required to maintain our applications and workloads, that wouldn't be sufficient. With this in mind, I'm going to also focus on how these changes will guarantee you either the exact same performance of your existing resources, but more often than not, these changes will actually offer you better performance. And then just to wrap things up with these 2 final bullet points, at a high level, the big picture problem that we often hear from organizations here at AWS is that they want to cost optimize, but they most of the time don't have the engineering bandwidth necessary to make drastic changes to their existing architecture. So the final 2 points that we're going to solve for is how we can recognize significant amounts of cost savings while ensuring we don't introduce engineering overhead by avoiding any architectural changes. So to ensure that your time is prioritized effectively, I wanted to take a second to walk through our plan of action and how we're going to solve for the problems I previously mentioned. And just to re-highlight that problem statement, it's how can we cost optimize while maintaining or getting increased performance using limited engineering bandwidth and introducing no architectural changes. To solve this, the first place we're going to take a deep dive into is Amazon Elastic Block Store. This is the best place for us to start as it's going to require the least amount of effort from any organization and is a very commonly used service. We're going to explore the benefits that GP3-based EBS volumes provide and why it's worth making the switch. I will also cover some unique features of GP3 and how this transition can be done with minimal effort. After Amazon Elastic Block Store, we're going to take a deeper look at why you should back your Amazon relational database instances and Amazon Aurora clusters with Graviton. We will look at this from the perspective of cost savings, then the increased performance, and then how to start the evaluation of what instances you could swap into. Last, requiring the most effort and very application dependent, we will explore migrating Linux-based workloads to Amazon Graviton-based Elastic Cloud Compute instances. During this section, I'll cover the cost savings potential, increased performance, and how to begin evaluating your current applications to determine which are ripe to be ported over to Graviton. So a primary reason for the creation of this webinar is so that you can take advantage of these recommendations and most importantly, put them into action. Throughout today's webinar, I will reference 4 tools that are worth getting familiar with while implementing these recommendations. The first tool is the AWS pricing calculator. This tool lets you explore AWS services and create an estimate for the cost of your use cases on AWS. And specifically for today, we'll be focused on how to use AWS pricing calculator to identify optimization opportunities and the potential savings associated with them. The second, which most likely you're already familiar with, is the AWS console or the CLI. When it comes to the actual implementation of these changes, they will be done in either the AWS console or the CLI. And for the sake of today, to make the demonstrations clear, all the screenshots that you'll see showing the walkthroughs are all going to be of the AWS console, but I want to make it clear that you can also make these changes through the CLI. Third is the porting advisor for Graviton, as this tool will help us evaluate what needs to be done on an application level to ensure the successful porting of your application to a Graviton-based Elastic Cloud Compute instance. And I will cover this in more depth later in the webinar. And then finally, we will use Cost Explorer. Cost Explorer has an easy-to-use interface that lets you visualize, understand, and manage your AWS costs and usage over time. And Cost Explorer will be key when it comes to tracking the cost savings associated with the changes being proposed in today's webinar. So to start this off, let's hop into the transition from GP2 Amazon Elastic Block Storage volumes to GP3 Amazon Elastic Block Storage volumes. So the question is why GP2 to GP3? And this is the first place that we're going to focus on because you can recognize significant amounts of cost savings overnight by upgrading your block storage volumes from GP2 to GP3. This is a fantastic place to start our workload optimization with no architectural changes. The first reason you should transition from GP2 to GP3 is the cost savings associated with the switch. GP3-based Elastic Block Storage volumes offer SSD performance at a 20% lower cost per gigabyte than GP2 volumes. So in theory, this should save you about 20% on your EBS costs right away. Even better, though, is that a big difference between GP2 and GP3 EBS volumes is that in GP3-based volumes, the storage performance is completely decoupled from the storage capacity. This gives you the ability to easily provision IOPS and throughput without the need to provision additional block storage capacity, thereby improving performance and reducing costs. This is a sizable contrast compared to GP2, where you likely needed to over-provision the storage of the volume to meet the performance throughput requirements that your application demanded. At this point, you're probably thinking to yourself that this all sounds great, but you're wondering, how do we actually implement this change? And thanks to Amazon EBS Elastic Volumes, you can increase the volume size, change the volume type, or adjust the performance of your EBS volumes. And Amazon EBS Elastic Volumes allows you to perform these actions without detaching the volume or restarting the instance. This enables you to continue using your application while the changes take effect. And during this transitional period, volume performance will be no less than the source volume performance. This ensures that your applications can continue running without a hitch as you make this transition and start to recognize these savings. So again, I want to make this actionable. So I thought it might be useful to quickly step through some screenshots of the console, highlighting the Modify Volume button, which leverages the Elastic Volumes feature. So the first step is navigating to the Amazon EC2 console and selecting Volumes on the left-hand side underneath Elastic Block Store. From there, we will select the GP2 volume that we're going to try to upgrade to GP3. And that can be seen on my screen here with that blue check mark. That is the volume that I selected. It's a GP2 volume. So we will select that specific volume, and then we'll click on the action dropdown in the top right-hand corner and select Modify Volume. And then after clicking on Modify Volume, we will be brought to this screen, and then we will click the Volume Type dropdown and select GP3. Lastly, we will configure the size of the volume and the performance of the volume. And then we'll confirm this by clicking on the Modify button in the center of the screen. And within 24 hours, your volume will be fully upgraded to GP3 with the exact specifications you defined on the screen, and it will maintain the same performance as the previous volume until this transition has been fully completed. And it's that easy to start recognizing that 20% of savings. And I thought to get an idea of the expected savings, I really wanted to provide an example. So on this slide, you're looking at screenshots from the AWS pricing calculator. And for this example, I wanted to calculate the costs of having 150 individual 1 terabyte EBS volumes. So on the left, I have made those specifications using the pricing calculator, as well as using GP2 EBS volumes. And on the right, I use the same specifications using GP3 base volumes. The final pricing for the GP2 volumes with this configuration came out to $15,360 per month, compared to the GP3 volumes, which came out to $12,288 per month. And to make this more realistic, I want to highlight the savings this change from GP2 to GP3 would result in on a monthly and a yearly basis. So as you can see on the far right-hand corner of this spreadsheet screenshot, the total monthly savings would be $3,072, and the yearly savings would be $36,864. So to conclude this section, the transition from GP2 to GP3 is the best place to start your workload optimization with no architectural changes. This change results in better performance and cost savings while ensuring no architectural changes or requiring significant engineering bandwidth. So now that we've covered EBS, I'd like to start talking about the transition of using Graviton-based EC2 instances with Amazon RDS and Amazon Aurora. And I want to mention that for today, we're just going to focus on Amazon RDS and Amazon Aurora, but the same changes that we're making to RDS and Aurora are applicable to other managed services. And just to give you a few, Amazon Memory DB for Redis, Amazon Elasticache, Amazon OpenSearch, Amazon EMR, AWS Lambda, and AWS Fargate can all benefit from these similar types of changes. So the second place we can look to optimize our workloads without architectural changes is swapping the instances we have backing our Amazon RDS and Amazon Aurora instances and clusters. The first point I'd like to bring up is the price to performance improvements that Graviton offers. To put some numbers behind it, for Amazon RDS, using Graviton-based instances can result in up to a 52% price to performance improvement for RDS open source databases, depending on the database engine, the version, and the workload. Similarly, when using Graviton-based instances to back your Aurora clusters, you can expect up to a 35% price to performance improvement, depending on database size. And to make this more clear, I will go over a pricing example in the coming slides. And with the price to performance improvements in mind, I believe the most important aspect of why you should use Graviton-based instances with your RDS and Aurora clusters is that no porting or code changes are required when migrating from Intel to Graviton 2 instances on Amazon RDS and Aurora. As you can imagine, this makes the transition far more seamless, as it does not introduce any architectural changes, nor does it require engineering bandwidth. And even if you are already using first generation Graviton instances, the swap to Graviton 2 instances is still worth it. Graviton 2 instances provide 7 times the performance, 4 times the number of compute cores, 2 times larger private caches per core, 5 times faster memory, and 2 times faster floating point performance per core over the first generation Graviton processors. Graviton 2 processors also feature an always-on and fully encrypted DDR4 memory and 50% faster per core encryption performance. And finally, let's briefly touch on compatibility. AWS Graviton 2 base database instances are available for Amazon Aurora PostgreSQL Compatible Edition and Amazon Aurora MySQL Compatible Edition. Graviton 2 instances are also available for Amazon RDS for MySQL, Amazon RDS for PostgreSQL, and Amazon RDS for MariaDB. You will need to ensure that your database engine version is compatible with Graviton 2 to make this change, and I will go into detail later in this webinar to highlight that in a little bit more depth. So now that we know why we should use Graviton 2 based instances with Amazon Aurora and Amazon RDS, let's go through the process of finding the right instances to swap into. And I would break this entire process into 3 steps. Step 1 will be going to the AWS pricing calculator and navigating to the RDS or Aurora with the specific engine you're running. And after we navigate there, we'll configure the exact instance that we're using currently. Step 2, we're going to determine the exact Graviton instance we can swap into using the performance specifications we found in step 1. And then step 3 is ultimately going to be actually performing the implementation of this instance swap. To dive deeper into each step, let's take a look at step 1. For the sake of clarity and this example, I have navigated to the AWS pricing calculator and selected Amazon RDS for MySQL, as seen on the left-hand side of this slide. On the right side of the slide, you will see the configuration page of the AWS pricing calculator for Amazon RDS for MySQL. And now that we are here, we can begin understanding the specifications of our current instances and the potential Graviton instance swaps that we can make. So on this configuration slide, let's first start by inputting our current instance type. For this example, it's going to be a db.r5.2x large, and take note of the vCPU count and the memory count. Please note the other configuration options, as this will be helpful when doing a direct comparison to the Graviton alternative. In this example, we're going to look at non-Graviton instances. Specifically, we are looking at 25 nodes of db.r5.2x large instances with a multi-AZ configuration with an on-demand pricing model. As you will see in the bottom of this screenshot, the cost of the current configuration with non-Graviton instances is $35,040 per month. Now that we have the technical specifications of the instances that we are currently using for our Amazon RDS for MySQL database, we can identify a potential Graviton alternative. The general way that I would approach this evaluation is by first looking at the size of the instance you're currently using. So in our example, it's a 2x large size, and the family of the instance we're using in our example. In this case, it's the R family. When it comes to looking for a Graviton instance that can be swapped, for the T family, the C family, R family, and M family of instances, there should be a direct Graviton alternative. At the time of recording this webinar, the latest generation family of database instances is the 6th generation, except for the T family, which is on the 4th generation. So the first step will be ensuring that we are identifying the latest generation of instances. So in this case, rather than inserting an R5 instance class, we will use R6, so that this is the R instance family, and specifically the 6, which is resembling the 6th generation. Then, to ensure it is a Graviton instance, we will have a G appended to it. So as you can see in the screenshot of the pricing calculator on the left, you will select the db.r6g.2x large instance. As we're looking for the latest generation of the R family of instances, using a Graviton-based instance with the size of 2x large. After selecting the proper instance, you can ensure it has the same technical specifications as your current instance, as you can see on the screenshot on the left-hand side. Again, this process can be repeated for the T family, the C family, R family, and M family of instances. And to be clear here, it has the exact same amount of vCPU cores, which is 8, and memory 64 gigabytes. So this is the exact same performance that we would get from the original db.r5.2x large instance. And after selecting this Graviton instance, you will see that the monthly cost is now forecasted to be $31,353.50. And now you've successfully identified the exact Graviton instance you could swap into to meet your application needs. And the final step to transitioning to Graviton 2-based instances is the actual implementation. The implementation can be broken up into 4 distinct steps. The first step will be upgrading the database if necessary. As part of this step, you will determine if the current database version meets the minimum required version for moving to Graviton 2. If it's not, you will need to upgrade that database engine to the required minimum version. Step 2 will be modifying the instance types. During this step, you will determine your strategy and the order in which to modify your instances, and then you modify the instance class of your instances to the appropriate Graviton 2 instance using the strategy we just covered in the previous slides. Step 3, as soon as the modification has been made, you will begin a thorough testing period just to validate and confirm that your application is running as expected. At this point, I would expect all things to go as expected, and if so, the implementation is complete. But if the application is not performing as you would expect, you can roll back the changes if required. So to conclude the Amazon RDS and Amazon Aurora section of this presentation, I wanted to summarize the cost savings associated with the changes proposed using an example. In the previous slides, we reviewed the pricing calculator estimate for 25 individual db.r5.2x large instances for Amazon RDS for MySQL, with the technical requirements of 8 vCPUs and 64 gigabytes of memory. So using the db.r5.2x large instances, the monthly cost would be $35,040. And using the db.r6g.2x large Graviton instances we defined earlier, the price would be $31,353.50 per month. This change would result in $3,686.50 in monthly savings. If we replicated the same scenario, moving from db.r5.2x large instances to db.r6g.2x large instances for our Amazon Aurora MySQL instances, the monthly savings would be $2,227. So if we made all of these changes, 50 instances in total, across our RDS and Aurora footprint, it would equate to $5,913 in monthly savings and $70,962 per year. So in conclusion, backing your Amazon RDS and Amazon Aurora instances with Graviton 2 is a great workload optimization that requires no architectural changes. As discussed, these changes can result in significant amounts of savings and increased performance, all while requiring limited engineering bandwidth. And in this final section of the webinar, we will cover the last way we can optimize our workloads that require no architectural changes. This optimization will explore leveraging Graviton-based instances for Linux workloads. We just covered why you should be leveraging Graviton when using Amazon RDS and Amazon Aurora. But AWS Graviton-based EC2 instances also offer substantial advantages for your compute-based workloads. First and foremost, AWS Graviton-based EC2 instances offer up to 40% better price performance over comparable current generation x86-based instances. Graviton-based EC2 instances can be used to satisfy a broad spectrum of workloads, such as application servers, microservices, video encoding, high-performance computing, electronic design automation, compression, gaming, and more. Graviton-based EC2 instances also feature capabilities that enable you to run cloud-native applications securely and at scale. AWS Graviton 3 processors feature always-on memory encryption, dedicated caches for every vCPU, and support for pointer authentications. EC2 instances powered by AWS Graviton processors are built on the AWS Nitro system that features the AWS Nitro security chip with dedicated hardware and security functions and have support for encrypted Amazon Elastic Block Storage volumes by default. AWS Graviton processors are supported by many Linux operating systems, including Amazon Linux 2, Red Hat Enterprise Linux, SUS, and Ubuntu. Many popular applications and services for security, monitoring and management, containers, and continuous integration and delivery from AWS and software partners also support AWS Graviton-based instances, thus giving you the ability to run these workloads more efficiently on the cloud. For those who may be concerned about their carbon footprint, AWS Graviton 3 processors, just like Graviton 2, are more energy efficient. Graviton 3-based instances use up to 60% less energy for the same performance than comparable EC2 instances. And similar to how we identified the right instance types for Amazon RDS and Amazon Aurora, we will use a similar strategy when identifying Graviton-based instances that can meet our compute requirements. The best way to approach this is using the AWS pricing calculator and navigating to the Amazon EC2 section and selecting Configure. From here, we will import our current compute requirements, such as the memory, vCPU, and networking, to identify better price to performance-based instances. As I previously mentioned, Graviton-based instances will have a G appended to the family name of the instance. As in the screenshot on the right-hand side, you can see that we have the T4G.nano selected. By leveraging the pricing calculator and inputting your compute requirements, you can identify the best possible instance swap. So this is a critical point when evaluating the porting of applications from your Linux workload to an ARM64 chip architecture. And I want to be clear that AWS Graviton processors do leverage an ARM64 chip. So your teams will need to evaluate the portability of your current workloads. So to make this easier, please refer to the chart on this slide to get a high-level categorization of effort required to port an existing application so that it can be run on a Graviton-based instance. As a general rule of thumb, the more current your software stack, the better. And this chart can be used to help your teams get an understanding of the engineering bandwidth required to perform a successful port. And the final tool that I will mention before concluding with an expected savings slide is the Porting Advisor for Graviton. The Porting Advisor for Graviton is an open source command line tool that analyzes source code and generates a report highlighting missing and outdated libraries and code constructs that may require modification along with recommendations for alternatives. It accelerates your transition to AWS Graviton-based instances by reducing the iterative process of identifying and resolving source code and library dependencies. The tool currently supports C, C++, Fortran, Go, Java, and Python, and can run on x86-based and ARM64-based machines. And as you can see on the right-hand side of this slide, this is an example of some of the findings that may come out of running the Porting Advisor for Graviton on your application. The Porting Advisor for Graviton is a great way to get a firm grasp on the amount of engineering bandwidth required to make a successful port. It provides a clear indication of where to start. To conclude the leveraging Graviton for Linux workloads, I wanted to provide an expected savings example. In this example, I've priced out 25 T3.large instances, 25 C5.large instances, 25 R5.xlarge instances, and 25 M5.2xlarge instances with an on-demand pricing model. After using the pricing calculator to gather the pricing estimate, the total cost for all 100 of these instances monthly would be roughly $16,227.90. And then I priced them out using the Graviton alternatives for the same size instances. And if you were to port your applications from the original instances to the Graviton alternatives, it would cost you $12,288.10 per month, resulting in $3,839.80 in monthly savings and $46,077.60 in yearly savings. This is the final example of a workload optimization that requires no architectural changes and requires limited engineering bandwidth depending on the application. Lastly, I want to summarize today's presentation, and specifically, I want to leave you with 3 places to take action in order to recognize some of the benefits that I mentioned today. And I purposely organized these in the order of required effort. So the first place that I would recommend starting is upgrading your existing GP2 EVS volumes to GP3, as this again requires the least amount of effort and you can see significant savings theoretically overnight. Secondly, I would recommend swapping the Amazon RDS and Amazon Aurora underlying compute to Graviton-based instances or the latest generation instances, depending on your database engine. Last, and this requires the most amount of effort and is very application dependent, I would migrate your existing Linux-based workloads to run on Graviton ARM64-based Amazon EC2 instances. And this will take maybe a longer-term roadmap, but the benefits in that long term will be significant and most definitely justify the switch. Again, these modifications can help you optimize your AWS costs without having to introduce any application re-architecture, system re-architecture, or engineering overhead. And to learn more, I do recommend looking at that link at the bottom of this slide. This actually links to the blog post that I created that actually lays out all of this information so that you can do further research if needed. Otherwise, thank you everyone for taking the time to view this webinar. And if you have any questions, please do reach out to the email that's on this slide. Otherwise, thank you again.